Okay, in this video I wanted to talk a little bit more about Green's theorem and something called the divergence theorem in the plane. Okay, if you remember, we discussed in the previous video Green's theorem over a simply connected region with continuous partials, that we can say this, right? Okay, the line integral around the boundary of the region, m dx plus n dy, is the double integral over the region n sub x minus m sub y dy, okay? dA. Let's take this example here. I've got y equals x squared and y equals 4x, okay? And you can see that this is going to create this little region right here. I'm going to call this part with the parabolic part, I'm going to call C1, and the linear part I'm going to call C2. You can see the direction in which we're traversing this relative to that particular region would be indeed the positive direction. Okay, you remember area I had in the previous video. Area is 1/2 the line integral around the boundary of this particular expression. Okay. Alrighty. Let's go ahead and think about computing the area then. Okay. Let's do it sort of the old-fashioned way first with a double integral. You can see I'd be going from what? X squared up to 4x on the inside, and x would go from what? 0 to 4. So this would be an expression for the area there. And if you actually integrate that, you get 2x squared minus 1/3 x cubed. Going from 0 to 4, I get 32/3 for the area. Okay, let's go ahead and use the other method here. Now you remember this is just my shortcut method here. Okay, in order to do this, what I'm going to do is actually integrate over C1 and C2. Remember, C1 was the parabolic part and C2 was the linear part. Okay, so you remember this works out to what? X dy minus y dx, okay, in both cases. It's just a way to remember this. If you don't like memorizing it that way, you can certainly memorize this. Okay, now what is over the parabolic part, C1, y is x squared, so differential and changes in y are the same as differential changes in x squared. So that's what I've written right there. That's really going to be what? 2x dx. Okay. Y itself is x squared, so I just substituted that in. And the limits for x were what? From 0 to 4. Okay. We'd be traversing in the positive direction as x goes from 0 to 4. Okay, my drawing's not that good, but should be reasonable. Okay. So that looks good. Don't forget your half out front. Okay, plus 1/2. Now here, y is 4x, so I've got what? I replace y by 4x everywhere. Okay, there and there. But you got to be careful that you remember that C2 is being traversed. What would be if I projected it down onto the x-axis in the negative direction? See the direction that the arrows are going? So in fact, x is going from what? 4 to 0. It's going to backwards, okay? So it's going from 4 to 0, okay? Now here, when I took the differential changes, that's 2x dx, okay? And here, the differential change in 4x would be 4 times the differential change in x, okay? Notice here on this part, nevertheless, these drop out, okay? Those totally drop out. And here I'm dealing with 2x squared minus x squared dx, so that's just x squared dx. Don't forget the half out front. So I've got 1/2 the integral from 0 to 4 of x squared dx. So that's 1/6 x cubed from 0 to 4. That's 64/6 or 32/3. Okay, so we got the same answer in either case. Just illustrating once again that we can find areas using line integrals. Remember, that came directly from Green's theorem. Okay, now I'm going to do something else here. Let's just say I was going to perform this line integral around the boundary of R. Okay, the following quantity, some negative n dx plus m dy. Okay, just pulling this out of my hat here. Okay, well, according to Green's theorem, then what should it be? It should be the derivative of the function that's on dy. Okay, don't get hung up with what m and n are. Okay, it should be the function that's sticking here on dy, which is m. Okay, m sub x, right? The derivative with respect to x. Okay, so that's that partial derivative. Minus what? The derivative of the function that's on dx there. Okay, subtracting the derivative of that with respect to y. Okay, so that would be m sub x minus n sub y dA. Okay, this is coming directly off of Green's. Okay, now I'm going to, by the way, assume that you'll see this is a convenience here in just a second. M and n, like usual, for my vector field. Okay, that's F. What does this boil down to? Ooh, that is what? M sub x plus n sub y. Okay? I know what that expression is. That's the two-dimensional version of what? Divergence. Remember divergence? All right? Sometimes we wrote it as del dot f. Okay? So that's that operator, quote-unquote, dotting on f. But it amounts to this, right? M sub x plus n sub y, assuming that f is given that way. Okay? So I could call that the divergence of f. So this is actually the divergence of f. So what we have here is that this line integral is the double integral over the region of the divergence. Okay? Now, before I write something else here, let's consider this. If I've got this curve C in the counterclockwise direction, okay? Did I write clockwise? Counterclockwise direction. Okay, dx over ds, right? dy over ds. That was our unit tangent vector. Remember that? Okay? And if I actually take the cross product of that with k, okay, you see that? That would be this vector. If you like your ijk's in here, like some people do. I'm using that particular formulation. But you end up with this vector. Okay? Okay? T cross k is dy over ds, negative dx over ds, comma 0. Okay? And this is more readily written since the k component is 0. dy over ds, negative dx over ds. Okay? This is actually an outward pointing normal. Okay? This is an outward pointing normal. Notice that if I dot this with what? My t hat, okay? This is, by the way, clearly a unit vector because my parameter is what? S, okay? So this goes back to the second chapter that we looked at in the book. But anyways, this is going to be outward pointing, and it's normal. The dot product of these two vectors, n hat and t hat, as you can see, will be, in fact, 0. Okay? Now let's go ahead and look at this expression that we just showed above. Okay? So I've got this line integral, negative n dx plus m dy is the double integral of the divergence over the region R. Let's just take a quick dot product here. I want to show something. F dotted with n hat here would be mn dotted with dy over ds, negative dx over ds, and this ends up being m dy over ds minus n dy over ds. Okay, so it's looking awfully familiar to what we have up here. So this thing could be written this way. So our line integral is actually this. F dotted with the outward pointing normal, ds, okay? Now remember s is what? Okay, good theoretical parameter, but it's arc length, right? So we're integrating in the positive direction around the boundary. This is the double integral of the divergence, and some people will call this the divergence theorem in the plane, okay? The divergence theorem in the plane, okay, because of this presence of the divergence. Okay, This thing is sometimes called the flux across the boundary. This thing. Notice you're taking the components around the boundary, the components of f in the outward normal direction. Okay? For all the outward normals. Okay? You're just considering integrating over ds, right? Those components of f that point outwards. Okay? From the region, that's flow across R, or flux across R. Flux is the typical word. It's kind of archaic in some ways. Reminds us of 19th century here. But you think of this as how much of the field is actually flowing across the region, okay, or out of the region. This is sometimes called circulation around the boundary, where we go what? We consider the part of f that is tangential, okay, and integrate that all around the boundary of the region, okay, and that's this guy, okay, mdx plus ndy, okay. Now if you think about that, that was our original formulation for the line integral using Green's theorem, okay. That was about circulation, but if we talk about flux going across the region, the boundary of the region here, what are we going to be dealing with? Divergence, okay. Let's talk about these planar theorems then, okay. Here's how some people, do you remember this? I did this before here. Some people like to write this. It's exactly the same as the curl of f dotted with k, so there's an exercise for you, okay. I actually mentioned it the previous time, dealing with Green's theorem, but this is the circulation theorem, okay. So this is the circulation. So this is essentially Green's theorem, okay. And then if you're talking about flux, this is actually a twisted form of Green's theorem then, because that's where we got it from. But the flux is this, and you're performing the double integral of the divergence, okay. Notice both of these second integrals, I mean, these are all scalars now, okay. I've had students mess up and start, forgetting the dot products in here represented scalars. But anyway. Okay, so there's a couple theorems here. Let's take some examples. Okay, my region is what? The unit disk centered at the origin. Okay, so there's my R. My field F is very simple, just xy. I want to find the circulation and the flux. Okay, using Green's theorem and the divergence theorem. Okay. Let's talk about the curl of f, okay? So you remember this formulation here? Again, if you like the ijk's in here, okay? Okay, so if you just start working out those partial derivatives, you're going to find the curl is actually 0, okay? The curl is 0, so when I dot it with k, I actually get 0, okay? So here we've got the circulation is the double integral over r of 0, so that means it's 0, right? So that means around the unit circle, you've got cancellation ultimately for one part of the curve compared to the other part for that particular field, okay? And here we've got the flux, okay? Double integral of the divergence of f, okay? The divergence of f is very easy. I just wrote it in there. Let's remind us what this was. Compute the divergence. Remember that is a scalar. Differentiate the first function, right, the m, with respect to x. What do you get? You get 1. Differentiate the second function. That's what we're calling n. With respect to I, that's also 1. Add them together, you get the divergence. That is 2. Okay? So the flux is the double integral of 2 dA, so that's just twice the area of the circle. But the area of the circle, because it's a unit disk, the area is pi, right? Pi r squared, pi 1 squared, so it's 2 pi. Okay? So there we go. We computed the flux across this thing. And then we've got, for some reason, I wrote those two at the end. Okay? Alrighty. Well, I hope you understood some of this stuff and are able to do some of those problems that remain that I've assigned. Okay, stuff shouldn't be too bad.